We've been talking about synthetic division, and we've already done a couple problems. Let's try one more. There's one thing that's different about this problem than about the previous two examples from the last video. So if we look, we are going to divide x cubed minus 4x squared minus 5 by x minus 3. So we know we always take from the x minus 3, the opposite of whatever that number is. So since it's negative 3, we're going to use positive 3. And we write down the coefficients of our terms from the dividend. So we have 1 from the x cubed, negative 4 from the x squared. Now here's the important part. We're missing an x term completely. So we have to put a 0 coefficient for the x term, and then the minus 5. So this 0, super important. If we leave it out, we will get messed up. So we put in a 0 because, again, there was no x to the first power term in the dividend. Otherwise, it's synthetic division like normal. So we bring the first coefficient down, multiply it by what's in the box and put it under the next coefficient. And then we add, and then we can get in our little rhythm. So multiply, add, multiply, add. And so what do we have? The dividend, x cubed minus 4x squared minus 5 equals our quotient, which is x squared minus x minus 3 times the divisor, x minus 3, minus 14, because our remainder is negative 14. Now, if we multiply that back out and add our remainder, so if we do this, evaluate this, or simplify, sorry, we should get back to our our dividend, excuse me. And if you want, you can multiply this out and see that that's the case, but you don't have to. So that brings us to two different theorems. And I am going to cross both of these boxes out because I don't like the way they're worded. It's another one of those things I need to change and haven't done yet. But let's talk about these. So the remainder theorem says this. If we have a polynomial that we're calling f of x, so it's also a function. If f of x is divided by x minus c, so a linear divisor, then the remainder is the function evaluated at that c from our divisor. So let's look at an example of this. If we go back to part A from example 1, we took 3x squared plus 2x minus 1, and we divided it by x minus 2. And when we did that, we got, the important part here is our remainder was 15. So what the remainder theorem says is if we evaluate f of 2, and the f here is our dividend, so this is f of x. If we evaluate that at 2, we should get 15. Let's see if that's true. So 3 times 2 squared plus 2 times 2 minus 1. That's 3 times 4 plus 4 minus 1, which is 12 plus 4 minus 1, which is indeed 15. So this is useful to know. And this is going to be even more useful when we get to chapter 5, because it's going to help us determine what's going on with our functions that we're going to be looking at. Okay, let's scroll down. I know you guys are probably out of paper if you're printing, but write this somewhere. Let's do the factor theorem. So the factor theorem says, again, let f of x be a polynomial function then x minus c, our divisor, is a factor of our dividend if and only if f of c equals 0. So what this says, remember when we go looking for x-intercepts, we have to factor our polynomial. We mostly have done this with quadratics so that we can determine where the function equals 0, our y value is 0, and get our x's. This theorem right here is going to help us with that. So if we go back and look at part B on example 1, we had 2x to the 5th plus 5x to the 4th minus 2x cubed plus 2x squared minus 2x plus 3. And we divided that by x plus 3. If you recall, we got a remainder of 0. So if we plug in -3, because that's what our c here is, and evaluate this function, we get 2 times -3 to the 5th plus 5 times -3 to the 4th minus 2 times -3 cubed plus 2 times -3 squared minus 2 times -3 plus 3. And if you put that just like that in your calculator, that's going to equal 0. that tells us that we know that 2x to the fifth plus 5x to the fourth, etc., is evenly divisible by x plus 3. So we can rewrite this whole mess as x plus 3 times whatever our quotient ends up being, with no remainder. Again, this is important because it's going to help us figure out our x-intercepts when we have functions that are not easily factorable, like a quadratic is easily factorable. All right, that's it for synthetic division. This is really going to come back at us in 2 more sections. We're going to do 5.1, sorry, 5.1, and then we'll go on to 5.5. So 5.5 is where the synthetic division and these 2 theorems we just covered matter to us.